Okay, so this second to last section in chapter 6 is going to go back to some of the stuff that we did actually a handful of chapters ago when we talked about properties of exponents. Like if you did x squared times x to the third, you would add the exponents. All those different properties like that. I think there were 7 or 8 of them at the time. But we're going to talk about this new type of exponent called a rational exponent. And remember, rational numbers are like fractions. So instead of dealing with exponents that are whole numbers, we're going to be dealing with exponents that are fractions and talking about what that means and how it connects to the stuff that we've been doing the last handful of lessons. Okay, so if we see something like this first definition, b and then raised to the 1 over n power. So b is the base and then the power would be 1 over n. That's actually equal to the nth root of b. So raising something to like the 1/3 power is like the cube root. Raising something to the 1/2 power is like the square root. The 1/4 power is like the 4th root, etc. So let me give you a little proof. Just very quickly so that you can see that they're the same. All right, so this thing, I know if I take this thing right here, I know if I raise it to the nth power, I'm supposed to get back to b. That's just the way that this thing works, because the nth root and the nth power are inverses of each other, so they leave me back with b. So if these two are the same, I should get the same thing when I raise this to the nth power. So let's say I take this thing and I decide to raise it to the nth power. So now bringing some of our properties of exponents, if I take a power and raise it to a power, I'm supposed to multiply them. So my new power would be 1 over n times n. The n's would cancel out and I would have just a b to the first power, which of course is b. So hopefully this shows you that those are in fact equal. It's just kind of a notation sort of thing. 2 different ways to write the exact same thing. So example 1, we're going to practice writing them back and forth, radical form, exponential form. This is radical form, this is exponential form. So writing a to the 1/5 in radical form. 1/5 means you're taking the 5th root of a. Okay, so how about the 8th root of c in exponential form? If you're taking the 8th root, that means your exponent would be 1/8. Okay, so just a little back and forth here. Now these ones, C and D, these ones are a little different because instead of the just the 1/4, we have these 7/4. So here's how it works. The 1/4 part still takes the 4th root, but I actually still have this exponent of 7. So underneath the 4th root is d to the 7th. That's the only change really. 1/4 technically meant I had like an a to the 1st left here, and I don't ever write the 1st power. So having the 7 in the numerator just means that I have a power of 7 left here. So this one's really similar. C was already to the -5th power, and then taking the cube root means I have a 1/3 in my exponent. Okay, so just a little bit of practice there. We're going to be going back and forth a little bit. Remember one thing when we were talking about our rules of exponents, we also had rules for negative exponents. Let me just remind you really quickly. If I had a base and it was raised to a negative exponent, remember that means that you flip it down to the denominator. Okay, so it's the same thing if you have negative rational exponents. So we'll see a couple of examples like that. So this thing, negative 3,125 to the -1/5 power. First of all, we're going to rewrite it using this property right here. It's going to be 1 over and then -3125 to the +1/5 power. Because if you flip it, that power actually does become positive. And then remember what this means. The 1/5 power means I'm taking the 5th root. So in the denominator, I now want to switch to the 5th root of -3125. Okay, so this is like what multiplies by itself 5 times and gives me 3125. Remember, raising something to the 5th power, you're dealing with very, very, very big numbers here. And I gave an example in the notes, a couple sets of notes ago, that if you raise something like 10 to the 5th power, you get 100,000. So it's got to be something that's less than 10. Now, 2 is out because we know what 2 to the 5th is. We actually also know what 3 to the 5th is. I'll give you a clue. It's 5. That should make sense. Like 5 times 5 is 25. Times 5 again is 125. Times 5 again is 625. And if we multiply by 5 one more time, we get 3125. However, this is negative. All right, so the fact that it's negative means it was actually a -5 that I was multiplying out. So just throw that negative out front rather than keeping it in the denominator, and we've got our final answer there. Okay, another one of these. This is really similar to what we were writing up here. If I have the 3/8 power, the 8th part means I'm taking the 8th root, and then I have 256 to the 3rd. Okay, I don't know about you, I have no interest in raising 256 to the 3rd power, because that would be 256 times 256 times 256. We're talking about a gigantic number here. Okay, so we've got options. Rather than taking or using the 3rd power first, then taking the 8th root, we can actually take the 8th root first and then raise it to the 3rd power. This is one of those weird things that it actually doesn't matter what order you go in, you'll still get the same answer. So if we look inside the parentheses, the 8th root of 256, something that multiplies by itself 8 times. Again, I'll use the example of 10. If we multiply 10 by itself 8 times, we get, 100 million, I think? So it's got to be a number that's much smaller than 10, and it's actually 2. You can always double check that on a calculator. All right, so the number I just simplified this to ended up to be 2. So we know 2 to the 5th is 32, so that means 2 to the 6th is 64, 2 to the 7th is 128, and 2 to the 8th is 256. So what I had in parentheses simplified up to be a 2, and then of course 2 to the 3rd gives me 8. So if for some reason we had decided to raise this to the 3rd power and then took the 8th root, we would get 8. But doing it this way was just a little bit easier. Okay, so we've seen kind of a couple things that these rational exponents can do. I want to write a little summary, kind of explains what we were just doing here. If I have b and it's raised to the x over y power, we have a definition for 1 over n, but we want to talk about what happens if you do have a number there, like the 3/8 power or the 7/4 power. So if you have this, you've got two options. You can either put b to the x underneath the y root, whatever that is, or we can do what we just did right here. We can take the y root of b, take what we get, and then raise it to the x power. I promise you, you will get the same thing either time. Okay, so keep this notation in mind when we're trying to simplify up some of our exponents that we're dealing with. Okay, example 3 is a story problem. We're going to be using a formula that we're given right here. So suppose a gallon of milk costs $2.99 now. Well, it seems fairly accurate. How much would the price increase in 9 months with an annual inflation rate of 5.3%? We've got this econ formula right here. C represents the future cost, that's what we're trying to find. C, little c, represents the current cost, so that's $2.99, so that's little c. R is the rate of inflation, that's the inflation rate right there, and then N is the number of years. So 9 months isn't a number of years, but we'll talk about that in a second. So C equals, little c is $2.99, and then in parentheses we have 1 plus R. So we don't write 5.3 because that's a percentage. Do you guys remember, hopefully, converting percentages into decimals? So it's actually 0.053. That's how you write 5.3% as a decimal. And then you raise it to the n power. N is supposed to be the number of years. 9 months is 3/4 of a year. So we're going to plug that in right there. Okay, so we've got that all set up. For some reason, I thought it'd be a good idea to not have a calculator right now. So I'm going to do this on my phone calculator. Okay, so let me start from the inside here. So 1 plus 0.053, we get our answer there. Then we raise it, so we've got this button right here. We raise it to the 3/4 power, so 0.75 equals, then multiply by $2.99. Excuse me. So we end up with a price, and of course, since it's a price, you want to round it to 2 decimal places. So $3.11 is what we're going to round that to. Now you always in story problems want to make sure that you're answering the question. The question was, how much would the price increase, not what is the new price. So going from $2.99 to $3.11 means the increase was 12 cents. That's the answer that they want. So always make sure you're reading questions carefully. Okay, so let's flip over, see what else we've got going on here. So now we're going to simplify some expressions. So we've got these properties that we talked about before, and the stuff that we talked about in 6-1 was simplifying up the operations. Sorry, that's not supposed to be 6-1. I don't remember when we did rational expressions, maybe 4-1. There's a couple of things that are very, very, very important. One that I mentioned down the front, always remember that negative exponents get flipped. So if you have negative exponents in the numerator, they get flipped down to the denominator. If for some reason you have negative exponents in the denominator, you would flip them up to the numerator. And then one of our rules, which I don't know if we've talked about this in a while, but one rule of exponents is that any exponents in the denominator must be positive integers. Meaning whole numbers. Okay, so 1, 2, 3, can't have negative numbers, can't have fractions, because remember, fractions technically represent square roots or cube roots, something in radical form, and one of our rules from the last section was that we're not allowed to have radicals in the denominator. So unless my exponent is an integer, I'm breaking that rule that we set for ourselves in that last section, okay? So we're going to simplify these expressions here. So p to the 1/4 times p to the 9/4. I'm going to write this out. So p to the 1/4 times p to the 9/4. Remember, if I'm multiplying base times base, I add the exponents. So I add 1/4 and 9/4, and I get 10/4. Okay, first of all, I'm going to reduce that down. 10/4 reduces down to 5/2. And then p to the 5/2 is the same as the square root, because the index is 2, of p to the 5th. Okay, so that's what you write as your final answer. It is the square root of p to the 5th. That 2 in the denominator becomes the index when I set it up in radical form. All right, another one here, r to the negative 4/5. Okay, so this first of all gets flipped. That was my first rule that I just wrote at the top of the page. However, my second rule says that exponents have to be positive integers. 4/5 is not an integer, it's a fraction. So I have to do that multiplication, that rationalizing the denominator stuff, that leads me to having a whole number. So let me kind of show you what I want my end result to be. I want just an r, like an r to the first in the denominator. So I have to figure out what I have to multiply by here. So here I have 4/5 power. The only power that's missing to get 1, 4/5, I need one more fifth in order to have a power of 1. So that's kind of what's missing in order to give me a perfect integer. And of course, I have to multiply by the same thing in the numerator. So when I multiply these together, I add the exponents. 4/5 and 1/5 is 5/5, which of course is 1. And then 1 times r to the 1/5, which is r to the 1/5. So r to the 1/5, remember, is the 5th root of r. And then I have just an r in the denominator. So even though I have the same variable appearing top and bottom, it's okay because I'm not allowed to have this fraction right here in the denominator, and that's a more important rule. Okay, one thing, remember to always use the least index possible. That's one of the things that we wrote in this chapter that we've seen. In order to be in simplified form, the index has to be as low as possible. So let's look at a couple more of these. We've got just 3 more examples and then a chart that kind of summarizes everything up. So the 4th root of 32, the cubed root of 2, we're going to use the stuff that we just talked about. We're going to write it in exponent form. So the 4th root means we've got 32 to the 1/4 over, and then 2 to the 1/3 is the way that we rewrite the cubed root of 2. Okay, so that's what we're starting with. So this, and I want to write, this is kind of weird, but 32, we want to write these in terms of the same thing. So this is a 2. We would like to rewrite 32 as 2. So this is 2 to the 5th. So instead of 32, I'm going to write 2 to the 5th because I'm working on simplifying that index down. And then I raise it to the 1/4. All right, then 2 to the 1/3. Now I'm going to simplify this up. So 2 to the 5th, then to the 1/4. I multiply those exponents together, and I get 5/4 over 2 to the 1/3. Finally, we can apply one of our properties that says if we have a base over a base, we can subtract their exponents. So I subtract 5/4 minus 1/3. So let's keep simplifying. Common denominator of 12. I'll have 15/12 minus 4/12. So I have 2 to the 11/12. Finally, that denominator of 12 becomes my index, and I'm taking the 12th roots, of 2 to the 11th. Okay, the 12th root of 2 to the 11th. I started to write that as an A because of our notation earlier. Just ignore that. It should be a 2. Okay, next one. Cubed root of 16x to the 4th. Okay, so still cube root. We're going to start to simplify the stuff up on the inside. So remember 16, we're going to write 16 as 2 to the 4th. So 2 is the base. We want the least. So 2 is the smallest base that we can write. So 2 to the 4th times x to the 4th. I know we did one method for simplifying these down the other day. We're going to use the rational exponent method this time. So 2 to the 4th x to the 4th. We're going to raise that to the 1/3 power, because remember 1/3 power and cube root are the same thing. Then I can raise them both to the 1/3 power, so 4 times 1/3 is this, and then x to the 4/3. Alright, so I'm going to continue to simplify these down. So 2 to the 4/3, I have 1 whole power of 2, and then a 1/3 power of 2 left over, times x to the 4/3 means I have a whole x, and then x to the 1/3 left over. Okay, so finally I have 2 times x that are kind of on their own, no powers attached, and then I have 2 to the 1/3 x to the 1/3. So that leaves me with the cube root of 2x. Okay, so same answer we would have done if we did our other methods, but I just wanted to show you an option. Okay, last one here, I have a y to the 1/2 in the denominator. I'm not allowed to have that 1/2 in the denominator, and so I'm going to rationalize it. And I'm going to rationalize it using the conjugate, just like we did in the notes with the last section. So the conjugate of y to the 1/2 minus 2 is y to the 1/2 plus 2. So I do that top and bottom. Okay, FOIL them all out. Y to the 1/2 times y to the 1/2. If I do 1/2 plus 1/2, I get 1. So that's actually just a y to the first, technically. Then outside, y to the 1/2 times 2. So 2y to the 1/2. Inside, 2 times y to the 1/2. And then last is 2 times 2, which of course is 4. Over y to the 1/2 times y to the 1/2. Again, add the 1/2 and 1/2, and we get to the power of 1. Plus 2y to the 1/2. Then on the inside I have minus 2y to the 1/2. Then negative 2 times positive 2 gives me a negative 4. So that's where I'm at so far. Now the reason that I chose to use the conjugate is because when I multiply conjugates together I always get something rational. No fraction exponents, no square roots. So in the numerator I have a y, and then this is a 4, y to the 1/2. And remember y to the 1/2 is the square root. Then plus 4. Then in the denominator, I just have a y minus 4. So y minus 4 is rational because it doesn't have any fraction exponents and it doesn't have any square roots. Okay, so we're done with those examples here. Let's take a look at this. This is something just that you can use to study, and we wrote some things down like that in the last section. So simplified form means no negative exponents. We've been talking about that. No exponents that aren't positive integers. We wrote that down too. Not a complex fraction. That means a fraction inside of a fraction. And then the index is the least number possible. We've talked about that as well. Okay, so our very last section that we've got coming up is solving radical equations. Okay, so we'll get to kind of put this stuff to work with equations.